It's our immense pleasure to welcome you all to the Namilinks. The upcoming 26th December is the 17th anniversary of the Indian Ocean tsunami. Therefore, we are dedicating this program to the victims of Indian Ocean tsunami. As we inform you, this project is an initiative of Coastline Marine Research Commission of INCOA. A detailed discussion on this project schedule will be conducted after talk 3. On behalf of Namilinks team, once again, I heartily welcoming all of you to the program. I'm requesting our audience to mute your mic until the presentation gets over. After that, you can get a chance to ask questions to the speakers. So we are kickoffing this workshop with a talk by Dr. Pedro JM Costa on tsunami deposit key features and challenges. A short introduction about Costa. Is a lecturer, the Department of Earth Science, University of Coimbra, Portugal. He is an author of more than 85 peer-reviewed journal publications, field guides, and books in geosciences. He's participated more than 25 research projects focused on signatures of extreme marine inundation, funding by national or international sources, including European Union, UNESCO, and national funding bodies from Portugal, Spain, and Brazil. He's also the reviewer for very prominent journals like the Holocene, Marine Geology, Sedimentary Geology, Nature Scientific Reports, Alien Research, Sedimentary Geology, Geomorphology and Quaternary Science Reviews, and Earth Science Reviews, Natural Hazards, Nature Communication, Earth and Environment, Geology, etc. Also, he served as an editor of 3 special issues for Sedimentology, Geoscience, eFrontier. So thank you, Professor, for accepting our invitation. So please share your presentation with us.
Thank you, Franco, and thank you all. Let me just minimize this. I think I would like to acknowledge your efforts and this Namilinks project and this meeting that you are organizing, because it's good when we have the chance to talk about our science and with so many familiar faces, but also with some new faces. For some reason, okay, let me just start. Okay. So on this presentation, I divided the presentation on some ongoing work that we are conducting, and I'll try to address a few things. But before that, I'll try to set up the evolution that tsunami geoscience has achieved over the last 30 years, from the initial papers from Brian F Atwater and Alistair Dawson in late 80s to the more recent ones that even this week Nature Communication already making scenarios for future conditions on tsunami events for the west coast of the US. So I'll try to set up a little bit of how this field of science evolved, and then I'll try to focus on 5 key areas that I think deserve an extra effort from us that work on this field of science. Of course, I have to acknowledge on my ongoing project on coupling onshore and offshore signatures of tsunami deposits and the institutions that I proudly serve. So I picked up two seminal papers from Brian F Atwater and from Alistair Dawson, my former supervisor. And when we look at those initial papers, there are some other papers that refer to tsunami imprints, but this one specifically discussed them as signatures of tsunami events. And from the sedimentological perspective, they provide already a lot of information. But over the years, we have evolved from identification to a more detailed and higher resolution analysis, and we can have a good review book on this one that was edited by Mike Sengel, Jessica, Simon, Ed, and others that I strongly recommend because it's up-to-date review of the state of the art. And then we even have predictions of future impact. So there's a lot of things changed over the last years, especially, and I have to say, because unfortunately we have several major events that led funding institutions to support research on this field of science. So 2004 clearly marks a change on the paradigm in terms of tsunami geoscience investigation. This morning, while I was, at least this morning for me, while I was preparing this talk, I just made two quick research on Science Direct and on Google. And I found out that if I type tsunami deposit, there's like 6,600 and something papers from 1987 till today that have been published with these keywords. And if we go to Google, there's more than 3 million references to this. And then I also went back and I look at myself when I was starting my master's, still with hair at the time, on a coastal lagoon in 2002, coastal lagoon in Portugal, when I started with a small Livingstone core doing this. And a lot of things changed, especially the way we look at the deposits now. Identification of the deposit is not sufficient nowadays. We need to reconstruct the event, especially when we talk at paleo events. Because we use geology, we use sedimentology because it will provide a large time window of observation. We can use other sciences to study tsunami events, especially the contemporaneous ones, the modern ones. We have instrumental data of those events, so it's much easier to perceive what happened. So these are vital events, are vital tools that will allow us to understand the past events. And especially in the Atlantic, where those events are fortunately not that frequent, we really need to rely on geology. So the more we can gain from experience from other events, the better. Of course, there's interfaces with other sciences, with history, archaeology, with physics, with meteorology, with other sciences that we can benefit from the data that is collected there. But one thing that also it's crucial in this field of science, in my opinion, is field validation. I've been starting to use models, and I don't know if there's a lot of modelers here, but models can produce almost everything that you want. The important thing is that they are validated by field data. So we cannot forget the importance of field data and always going back to that as the most reliable database that we have. From that, we can use models, and we can use them as a tool to demonstrate, and especially to I would say more to end users, it will be important that we use models because it will be a more visual interface that will facilitate communication. But we need to rely on field data, and then from that, use them to validate models that are being developed every day. Of course, one of the key issues that we always struggle to, and here we have images from the tsunami in Japan, 2011, from my hometown in Coimbra, some floods, and on the right images, there's Hurricane Leslie in 2017 that hit the central coast of Portugal. When we look to these extreme events, sometimes we try to, and we need to go back to the sedimentological record, and sometimes it's difficult to distinguish. And from the initial identification, then we pass to the differentiation of tsunami, especially tsunami and storm deposits. And that is still an important issue, and there's still a lot of questions going on regarding that. And I would dare myself to say that one key thing that we all need to consider is that in most cases, this is all site-specific. So we always need to have a good knowledge of the context that we are studying So we can really identify the tiny differences between extreme events that we are trying to analyze in a specific setting. Of course, the more we learn from modern events where we have more data, the better we will analyze the past. And the archives are typically, on the top left, you have an image of a Roman ruin in the coast of the Algarve, studied by some German and Portuguese colleagues. There's also the typical environments that we look for this type of extreme marine inundation signatures, which are low-lying, low-energy basins like lagoonal areas or estuarine areas. And even in a nearshore here with Lisa Feist, that is also here, also trying to look, we started looking at the nearshore, trying to find some evidences of tsunami deposits, initially using geophysics, but also now with some cores. So if I can summarize, and I just randomly selected 4 papers that were produced over time, and at least for me, they had importance as a good review of what had been tsunami geoscience had progressed, and the famous toolkit, etc. The key aspects that we should look for in tsunami deposits. I will summarize by saying that, and trying to simplify a little bit, that usually tsunami deposits are peculiar in stratigraphy. That's what can come up first. When we look macroscopically, we look at something and it's something that is not quite fitting the background stratigraphy. Then, and I stress this again, I think we should always have a lot of attention to the site that we are studying. We need to understand the sedimentological context, the geomorphological context, the hydrodynamic context, because these are key factors. Even the source area in terms of sediment, these are all key aspects that will contribute to the final, or to the deposit that we will find out. Of course, we typically also see a contrasting features in terms of paleontological content and geochemical elements when we compare the tsunami deposit with the under and overlying layer. There's another aspect that is also frequent, is that the composition reflects the energy of the process, of course. It tends to thin and it becomes finer inland. But is essentially the sediments that feed the deposit are essentially local source. There's very few description where you can find sediment that is not from the coastal fringe. It's not common that you find sediment that is transported from -200 meters deep to the coast. It can occasionally occur, but essentially the deposit that we are finding on those locations that I was mentioning, low-lying, low-energy basins, are essentially local coastal deposits. Of course, then we have to consider the geomorphological constraint as key for the type of signature that we find. If we have a narrow area with like a canyon, then of course the inundation will propagate further inland. If it's a flat basin or a flat bay embayment, then the deposit will not go so further inland. Of course, what we try to see is this mixture of, with increasing distance to the coast, we will see a decrease in energy, and that will be reflected in sediment transport. There are many other characteristics that are summed up on those 4 papers that I mentioned here, and on 50 more that also address these issues. But this would be like the very basic for a non-geological for public that has no geological background. This would be very basic features of tsunami deposits. And I'm just going to provide very quick examples of what we have done in the Portuguese coast, using some of the features and finding some of the features, and then changing from identification, then differentiation, and now retrieving information, trying to get to physical parameters of events, departing from the deposits, departing from the sediments, and making the sediments tell the story, reconstructing the event. So here on 1755, this is a coastal lagoon in South Portugal. And basically from the decrease of thickness, we were able to see how the tsunami deposit varied. And when we traced that back to the dune barrier and we saw the small depression that was caused by the tsunami inundation, we were able to see, I don't know if you can see my mouse, I hope you can, otherwise. But we were able to see that essentially the tsunami waves were only able to overcome or overtop, to be more correct, the barrier up to 10 meters high. So with basic information from the axis of the thickness decrease that we observed, we were able to pinpoint the area where the dune barrier was overtopped. And that information of the 10 meters was complemented with GPR information that we used. And then on those specific barriers, we saw erosional feature that we OSL dated, and it fitted the 1755 event. And this was 6 meter high. So based on the deposit, we were able to constrain the run up between 6 meters as the minimum that was eroded here, and 10 meters that we saw with a small depression on the dune. And this, we are talking about tsunamis where we don't have instrumental information, and that makes a lot of difference because we need to rely on the sediments to reconstruct the event. On another topic or another perspective was to determine the inundation phases. So when you look at the deposit, there's mud up here, mud at the lower contact as well, and essentially looks like a massive deposit. But when we analyze it at half centimeter resolution, we are able to see differences in geochemistry, micropaleontology, namely foranes, and also in terms of grain size using image analysis. And with that, we were able to establish 3 major inundation phases and 1 recovery phase. So we were able to see what was initially a massive deposit and then try to reconstruct that. So again, retrieving information from sediments and reconstructing the event. On the sediment source, just an example, and also focusing on phases, we saw that when we did a ratio between rounded zircon and euhedral zircon, we saw that euhedral was more present on the backwash phase, while rounded zircons were more present on the inundation phase of the tsunami event. And that had to do because zircons were in the beach and they were rounded because of normal sedimentary processes, coastal processes. So with that ratio, we were also able to distinguish backwash and inundation phase. Just another example how we got to flow depth and flow velocity from sediments. We had this small between cobbles and bobbles, size of watermelons to the size of, I would say, almost a car. And they were full of these protuberant petricular lithophaga, which is a bivalve. And they were covering the whole surface of the cobble or the boulder. And that meant, and these are typically from -5 to -90 meters deep, if the whole surface was covered, then it was highly likely that these boulders were transported in suspension, because if they were rolling, these small protuberant shells that you can see on the bottom right image would break. So with that information, we just applied simple sediment transport equations, and we got a maximum flow depth, we got a flow depth and a flow velocity. So all from the sediments, we are already reconstructing physical parameters from an event that we were not, from which we did not have that type of information. This is a very brief and subjective table summarizing a few aspects. What I would like to call your attention is that we need to be aware that typically the sedimentological record is biased toward the extrememost, at least in terms of tsunami deposits, I mean. At least that's what I have detected both on Portugal and in Spain, in Morocco, in Scotland, all over the Atlantic. I would say on this side of the Atlantic, I would say we only have the extrememost events. And that is something that we should also have in consideration when we are providing data to end users. But I think we do not fully understand today, or till today is the erosional signatures. We still struggle with erosional signatures. There's a lot of aspects that we need to explore in terms of muddy imprints of tsunami events. We recently realized on one of the most studied areas in Portugal, Martinhal, which is, there are several papers from Stella Kortkas and Alistair Dawson, there's a lot of work. We recently realized that maybe what we were considering the top of the deposit, because it was the top of the sandy unit, it's highly likely that it's not, and we have like a quite thick mud cap above it, and we disregard that initially because we were looking at just the contrast. So we need to increase the resolution also on these mud above the tsunami, what we consider initially as macroscopically evident the tsunami deposit. Then one thing that I think it's an opportunity is the inundation and backwash signatures, namely on the offshore. I think that the difference in pressure that the tsunami or the water column causes, it's highly likely that can move sediment, move slightly the sediment on the seaward direction, on the landward direction when the tsunami waves are approaching, and then have a more, I will not call it a turbidite, but more like a debris flow signature when we have the backwash. But that is something that needs to be explored. Then again, it's to go from the deposit to establish generation mechanism, and that will be crucial. I think we can address that if we extend the spatial distribution of our analysis, because I think typically a landslide generated event would be more unidirectional, while earthquake will have a larger and equal distribution of tsunami imprints. But that is something that I'm not sure and needs to be explored, because if you are working with civil protection, they will want to know if we can retrieve that information. Also, again, from deposit to intensity, then if we go back in time, in the case of here, in this part of the Atlantic, more than 5,000, we need to start playing with sea level. And that raises a lot of other questions. Again, I think the geophysical signature has not been explored sufficiently. We still have the question with the differentiation from other extreme marine events. And what I think would be a key issue, and that I think can allow this thing to differentiate from tsunami and storm events, for example, is that when we look at the images from Japan, we see that tsunami, the water was really full of sediment, was really dark. So it's not really, maybe the physics are not like water flowing with a few grains like we have in storms, but it's more like porridge. It's more like it's very dense water flow loaded with sediments. And of course, the imprints that we will see in sediments, the abrasion that we'll see on foreign tests will be different, in my opinion. And that has been also discussed already on some of the previous papers. The opportunities that I think will come up and have been already tested by a few colleagues is the offshore signature, trying to complement, especially on the shallow offshore, trying to complement the information. Then to go even into further detail into the internal structures of the deposits, trying to address as estimation, especially on boulder transport, because what we need to determine is not the age of the boulder, is the age of transport. And unless some of those methods are improved, we will still have a lot of questions that will be raised once we detect some boulder field, etc. Sorry. Regarding numerical modeling, it's an ongoing process that will improve with the improvement of and the extent of the databases that we will provide. I'm enthusiastic about empirical tests, although we will have lots of problems with scaling, etc. And I'll briefly mention on the final 3 or 4 slides of this long presentation, and I apologize for this long presentation. The conceptual model, and Lisa produced this one, of the offshore exemplifies the type of backwash signature that we would have, the locations where we would have the deposit. We would also have to play with storm wave depth and go to and look in specific depths. In the Portuguese coast, in this project with the German colleagues, what we have found is that usually the storm wave depth is around 15 meters deep, and we were able to trace the deposit with geophysical data up to 30 meters deep. And we were able to core and find the deposit from 60 meters deep to 120 meters deep. We found clearly deposits of what we think are tsunami events. That I cannot discuss on this presentation. The offshore also offers a lot of discussions. I think it's an opportunity because it's less disturbed by man, so the anthropogenic disturbances are much smaller, but also raises a lot of problems, and we should be aware of that. And I would say that we still don't fully understand the physics of backwash, and that is something that needs to be studied properly, so we can also hopefully understand better the deposits that we find. I'll not go and I'll not show this video. Sorry, the video just okay. And I was just going to show you some of the geophysical data that we collected here. It's hard to see, but core 19 is the one closer to the coast on the western profile. And you see like a dark black line that you can see on some of the locations. Once we did the core, there was really a deposit that was there. We used a really impressive research vessel, German research vessel Meteor. And then we used a small Portuguese one from the Navy, an old one, to do the geophysics. And we were able to trace where the larger ship was not able to go because it was too closer to the coast. And we were able to trace the deposit. Numerical modeling, there's a very nice review by Sugawara that I recommend that you try to address that. We tried to do this like back ray tracing and tried to see, there's a lot of questions regarding 1755 epicentral area. There's still a lot of doubts where it really was because there's no tectonic structure with enough dimension to cause the earthquake that is described. So we tried to fit different scenarios, the Marquês de Pombal fault, the Horseshoe fault, and a combined scenario of two, and tried to see which one of those scenarios fitted better with the tsunami imprint that we detected in the south coast of Portugal. So this is another discussion, but it's something that can be also useful for this. Then there's the internal structure. So we need to increase the resolution so we can see details. On this paper by Simon Folvard and Rafael, it's quite impressive how they reconstruct the inundation phases based on really detailed resolutions. I think we can all benefit from the major developments, and major developments in science are usually where the money is, and the money is in healthcare and it's in military. So if we can benefit from medical imagery, that would be good. I have done some experience with CT scan, and I'm quite impressed with the level of detail. Sometimes I find that we are getting into too much detail and we are seeing things that maybe are just details and are not relevant in terms of understanding the process. Of course, this has large cost and constrains the spatial distribution of this analysis when we have to do a lot of CT scans and other analysis. age estimation, of course, there's, I would just try to stress the problem of boulder deposits, because without good chronological constraint, and that's the advantage of looking at sandy deposits, is that we have a stratigraphical context. Without good age estimation, it's complicated to ascribe a boulder field to a tsunami or to storm. So it will always be questioned by someone, so it's not like conclusive argument. So we need to also try to improve this. I have no solution for this. I'm just raising questions that I think are key issues for the next maybe 5-10 years. Empirical tests, I'm really keen on this, but it's complicated. It's a mess in terms of scale. It's a mess in terms of what type of wave do you use. because there's too many constraints, but I think we can learn from it. And even in a small wave flume test that we did, we saw a concentration of heavy minerals from the initial population of grains that we saw. But it's really complex, and it needs some kind of approach between different fields of science. And to conclude my long presentation, and I'm sorry for that, I think I listened to a presentation of a firefighter that went to Haiti in 2010, 2009 after the earthquake. And I realized that despite all the effort and almost 20 years now working on this, I'm still not providing sufficiently good enough answer for the civil protection authorities. So I'm not giving them the numbers. I have too many questions. And when they describe the reality that they face, I feel myself small, and that my contribution is really small. So we need to have in mind that our field of science has 30 years basically, and there's a lot of work that needs to be done. And I'm encouraged you guys to pursue some of the avenues that I pointed. I'm sure the other speakers will also mention other opportunities. But I think it's important that we do not forget that we try to work for society. I'm paid for public institutions, so I work for society, and I need to provide them something. And I love to play with my quartz grains. I love to play with my sand and go to the SEM, but sometimes I wonder what type of answer am I providing? And this is just like a philosophical thought to end my presentation, and I apologize for taking just too long. Thank you very much.
Thank you very much, Professor, for your wonderful presentation. So
Thank you.
if you have any questions, you can quickly ask to Professor. Okay, then it's fine. So we can move ahead. I think there is no questions. Two questions I just from we have got from the that how we can predict paleo tsunami. I just paused. He is already discussed with that. And one question is from Ahmad Amrish, PV from Department of Earth and Environmental Sciences from Lakshadweep. So he's asking that the tsunami effect in small island groups. What is the tsunami effect in small island group?
That will depend on the small islands, if they're flat, or that will depend on the terrain. It's a complicated, it all depends on the context. So if we are talking about South Pacific and areas and small islands that are quite flat, of course, a small tsunami will have devastating consequences. But if we are talking about hilly, volcanic islands in the middle of the Atlantic, then it would be a different story. So that depends on the area specifically.
Yeah, thank you, Professor. Thank you. I think that.
Yes, sir. Yeah, I'm asking that question. That island related to Lakshadweep Island and Arabian Island, so Coral Island, and
Yes.
if it is the possibilities of tsunami from that island, that small group of islands. There's a chain of archipelago in Andaman, Lakshadweep, Chagor ridges. In
Arabian Sea.
Lakshadweep, Arabian Sea, Lakshadweep and Maldives is the chain of island. How it is possibilities to tsunami in this island area?
I'm going to acknowledge my limitations, and I'm afraid I'm not able to fully answer your question. I don't know exactly where it is located, so I'm afraid that I would be just speculating if I tried to answer your question. I'm aware of some papers that have studied tsunami deposits in the Arabian Peninsula, in Oman and other countries, and I can provide you those papers. But specifically on that location, I'm afraid I have no information, and I apologize for that.
So basically, we have two subduction zones. One is Makran subduction zone and Sumatra Andaman subduction zone earthquake
Yeah. Yes.
is the prominent threats to Lakshadweep Islands. So I think so. Okay, fine. So we can go ahead with our next presentation. It's our pleasure to introduce our next speaker, Professor María-Teresa Ramírez-Herrera. He's a full-time professor at UNAM, Mexico, and a visiting researcher at University of California, Berkeley. She is actively working on paleo-tsunami deposits, active tectonics and faulting, landscapes, both onshore and offshore, response to the subduction zone processes in Mexico and Chile. She published more than 80 publications in peer-reviewed journals and headed various national and international projects. Today, she is going to talk about the Mexican subduction zone and associated tsunamis. It's my honor to welcome Ramírez-Herrera for the talk. Professor, please share the presentation with us.
Thank you very much. I appreciate the invitation by you guys and the effort to put together a nice conference and workshop. So I'm gonna just briefly, because we're running out of time, acknowledge funding of my work by the University of Mexico, the National Science Foundation, and JICA, and the Mexican Science Council. So I'm going to talk about large earthquakes and tsunamis on the Mexican Pacific coast that is parallel to the Mexican subduction zone. And I also want to say that this is a product of several years. So I'm going to try to summarize some of the work. And also it's collaboration with many co-authors and also my students. Oh, it's not changing. Okay. So the Mexican, what I'm gonna briefly talk to, just an overview, is the Mexican subduction zone. Some of the results we have on the historic and the geologic evidence that we found there, and also some of the largest events along the Mexican subduction zone. And then I'm going to talk about the questions and the challenges that we face in Mexico, and the strategies and approach that we have used to face these challenges. And finally, I'm going to focus on the work that is ongoing and the future work. So, well, for those that are not familiar with the Mexico subduction zone, I'm just going to briefly summarize what's going on here. So in Mexico, we have, in fact, 4 plates, the Rivera Plate and the Cocos Plate that are subducting under the North American Plate. And further to the south, we have also the interaction of the Caribbean Plate. What you see here in these patches in color is the aftershock areas of some of the largest events of the last century and this century. And I'm just going to briefly show you the ones that are the largest, and also the ones that have produced tsunamis in the past. So this is the last 2 centuries. In 1932, we had an event, magnitude 8.2, and that produced a large tsunami. And then we had a smaller event in the same month, that was June 3rd, and another event in June in 1932 that also produced a large tsunami in this region of Jalisco and Colima. And more recently, in 1995, we had another earthquake, magnitude 8, with also considerable tsunami. And maybe some of you have heard about the big earthquake that devastated Mexico City in 1985. This earthquake had a magnitude 8.1, and it produced also a tsunami along the coast of Michoacán and Guerrero. And day after, there was an aftershock that also produced a tsunami further to the south on the coast of Guerrero. And well, more recently, we had events also on the coast of Oaxaca. I'm gonna talk about them later, and then also on the coast of Chiapas further to the south. No, sorry. So let me just mention this event. The 1787 earthquake is apparently the largest earthquake that has been found in historical records. And the estimated magnitude of this event is 8.6, and the rupture length about 450 kilometers long. That event, that earthquake, produced a tsunami that inundated the coast of Guerrero, near Acapulco, all the way south to Oaxaca, and also Chiapas. So it produced a large tsunami, and apparently also is the largest tsunami recorded in historical records. So what we see as a problem is that globally, the instrumental record of, I think it, probably we can, I mean, at least in Mexico, we have a very short record of instrumentals. In Mexico, the National Seismological Survey started in 1910 with only one station in central Mexico. So that means that we have only 110 years of seismic instrumental data. So that's a very short record. And so we might misestimate the seismic hazard and also the tsunamigenic earthquakes by just relying on instrumental data. And then the tide records in Mexico are also very short. The first tide record station started in 1942, and that was on the Gulf of Mexico, which is a Pacific coast and has no earthquakes. So this is a problem. So we had to rely on original historical accounts. And the historical accounts in Mexico, they back prior to the arrival of the Spaniards and the colonial time in Mexico. That was in the 1500s. But before the arrival of the Spaniards, we had also records by the indigenous civilizations at the time, as the Aztecs and others. And what we know is that in Mexico, the prehistoric, pre-Hispanic history already had an earthquake mythology. So for instance, the Aztec mythology already had a god that was named Tepeyolotli, and that was the god of earthquakes, right? And so they represented this god as a jaguar. And from the historical records, we also know that with this pictographic representation of earthquakes, this pictogram indicates an earthquake, and these numbers indicate the year. So we know that at least the Mexica people recorded at least 8 earthquakes of magnitude approximately 8.1, similar to the 1985 event prior to the arrival of the Spaniards. And then the Spaniards arrived in the 1500s, and they changed the way the Aztec people represented earthquakes. So what they did is to translate several of the documents from the local indigenous people, and they translated into all Spanish, all these records, but they changed the representation of earthquakes, and they used, for instance, to describe the earthquake length, they quantify it by the number of bridges and not pictograms. And they instead of using pictograms, they use this kind of paintings with the description of the event at the time. And curiously, they name each earthquake according to the name of the saint, because in the calendar, Catholic calendar, which is normal in almost all Latin America, each day has the name of a saint. So if the earthquake occurred, for instance, on the 28th March, that was the day of the Saint San Sixto, and they named the earthquake according to the name of the saint. So it was a little bit changed, but this is a representation from the Codex Tejeriano Remenesis. And in this representation, they indicate the year that in 1537, that was the year they call it, this year was 6 houses from 1537, and they made a description that there was an earthquake, and they basically provide all the details of the event. And we find a record that apparently, we found later that this record in Japan indicated a tsunami, but apparently the record is wrong from Japan. So we know there was an earthquake, but we weren't sure about the historical record for the tsunami. And so, as I was indicated that the largest earthquake recorded in historical records was the 1787 event. And that earthquake happened more or less between 11 a.m. and 12 p.m. And there was a series of earthquakes. This was a large earthquake that was felt mainly in the southwest coast of Mexico, and also central Mexico, and also on the Gulf of Mexico. The intensity was pretty high, and that's how Suarez and Albini come with a magnitude 8.6 approximately. And there was another event later, an aftershock of magnitude 7.3. We also took the task of looking at, I want to tell you that all these documents are in old Spanish. That is like reading Shakespeare, they're all English. So it's not easy to translate, but we had help from historians. And so we translated all these old documents into Spanish. And they describe that at the time in 1787, when the earthquake happened, there was also a huge tsunami. They didn't call it tsunami, obviously, but they describe how far inland this tsunami went and how high was the. I described that it was about 6 kilometers inland, the inundation, and and that was close to a place called Corralero. So we had to look also at all maps to find the location of the places that they describe as places that were inundated by this tsunami. Since they record the inundation as far as Acapulco, we also look for all maps to find also how far inland the tsunami inundation went. Obviously, there is also some, well, the maps that they did at the time, they gave us, well, the scale is not exactly, but they give us an idea of the locations that are described in the historical documents. That's for the history. And regarding, we used also took the task of looking at the geologic evidence of these large events. And we use the principle that everybody knows here, so I'm not gonna take some time here. This is a diagram by Lagos and Cisternas that describe the inundation of a tsunami after an earthquake. And so what I'm showing here is the location, let me go back, of this event. So I'm talking about, some of you are not familiar with the geography of Mexico. This is the Guerrero Gap. This is an area where we expect a large earthquake to happen. We don't know when. So because this area has had no earthquake since 1911. And so we have a gap here. So, and another gap here in the Tehuantepec zone. The area that I'm talking about is where the 1787 event took place, was near this area, the Corralero area. And here we represent with these dashes, orange dashes, what is estimated as the rupture area, 450 kilometers. So we took the task of looking for the evidence, geologic evidence of this event on this section of the coast. And focus, as Carlos, Pedro Costa was describing, we look carefully at the geomorphology, and also we look at the experience of Brian Atwater working on the Indian Ocean and on Plateau Island. And they found the evidence of tsunami deposits preserved on the swales between beach ridges. So we found this really nice setting of a series of beach ridges near the Corralero Lagoon that also matches with one of the description of the areas where that was more flooded inland. Over here, the historical descriptions indicated like 6 kilometers inland. So we were here making a transect, and we found, as I mentioned before, after Brian Atwater experience, a series of beach ridges. We use our LiDAR model also to map all these. There was sand dunes on the front, and then a series of beach ridges. So I will show you the evidence from here. And also the last point here, that is about 1.5 to 2 kilometers inland. So you can see that this is a really flat area with swales in between the beach ridges, and we were following these sand units along this transect. And then we took samples, correlated, and we found 2 suspicious units of tsunami deposits as far inland as 1.5 kilometers. And also we found geomorphic evidence of breaches in between the dunes on front, and also in between these beach ridges. They were, you can see here, breached, and this is a profile of the same place. So just to summarize what we found here, we found, we performed analysis of microfossils and also geochemical analysis. This is a summary and also grain size analysis, and then dated these events. And indeed, this event coincides with the 1787 tsunami. And we found another unit below that matches the 1537 earthquake described in the documents written by the Aztec people. They felt the earthquake, but we don't have the historical documents for this event because in 1537, the coast was barely populated. So with modeling, what we did, it was just to corroborate that we were looking indeed at tsunami deposits, and we were trying to test if the tsunami went as far using the rupture area proposed by Suarez and Albini. And with this model also we estimated if the coast could be uplifted or it experienced subsidence. So we were in fact in this using this modeling to test our results. And so finally, I just summarize quickly. I don't know the time, please make me a sign when I have to stop. So so we know we have for sure, we prove that it's not only the historical record, but we also have the geologic record of a large earthquake and a large tsunami in 1787, and another big earthquake and tsunami that occurred in 1537. So let me also give you that was it. So now we are focusing on this area, on the Guerrero Gap, because this is the area that, I mean, we just had this year, a couple of months ago, an event over here, magnitude 7.1, but it was outside the gap. In this gap, we have had no event since 1911. So that's the reason why we are working hard in this area, trying to find evidence. What we are doing is also talking to the people that experienced the 1985 earthquake and tsunami on this region. We found, we are collecting data from their descriptions. And then we also look at historical records and made a summary of the events that have been recorded for the Acapulco Guerrero area. So I mentioned the 1537 event also affected this area, the 1787, and we have other events. In green, you can show, over here we have already found evidence of tsunami deposits, this one too, and this one also. And these 3 modern events from 1799 and 2 events in 85. But this event is kind of problem because apparently there is no record in the seismograph, in instrumental data of this event. However, there is data of a tsunami. So the hypothesis that we have is that this event might have occurred due to a submarine landslide if there was no earthquake. So I already mentioned this. So I'm just gonna give you a tour on what we are working and the environments that we are working on. We are looking for evidence on estuaries, on mud floods like this one. Just remember, this is a tropical coast and sometimes difficult to work on, but we had good results. We are doing the geomorphic mapping previous to go and digging and do the exploration, and just a summary on the findings that we have in this region. So we have worked on the mud flats and the areas around the lagoons, and 3 different lagoons here in the Guerrero Gap, in Mitla Lagoon, Coyuca, and Tres Palos. And basically what we found, and this is not very common in Mexico, at least in instrumental data, that we found that there is tectonic subsidence occurring at the time of the earthquakes. We have a possible record that goes back to 3,400 GRBP at this lagoon in Mitla, and 3 probably tsunami events. And we find also archaeological evidence of subsidence in this lagoon. The archaeological site is underwater, and we explain this as coseismic subsidence. On estuaries, I'm just going to give you a summary. This is close to Zihuatanejo, northwest of Acapulco. And in this area, we look for the evidence, try to test if we could find the 1985 tsunami that happened after the big earthquake. And so also we look at historical records, records in newspapers, and also interviewed people at the time. As I mentioned before, we work with colleagues, students, and you can see here is Ian Hutchinson from Canada. And so we did several trenches and pits and recover slices of the trenches. And to our surprise, we found 2 events, not only the 1985, but another previous event in this area that was really nice. We dated this with lead 210, and indeed they are the events that match the 1985 magnitude 8.1 earthquake and the tsunami, and a previous event that happened in 1979. And this is in Guerrero. And we use multiple proxies because I will talk about the challenges working in the tropics. Over here we use grain size and geochemical also proxies and microfossils to determine the marine source for these 2 events. And now let me talk. I'm not sure if I'm going beyond time. Please let me know, because I don't have a clock here. So I was mentioning that we have in this section of the coast also instrumental data of large events, the largest of which happened in 1932, and it was a magnitude 8.2 event. And so we are look for this section. In fact, the tectonic setting is different. We have here the subduction of the Rivera Plate under the North American Plate. This is a younger plate than the Cocos Plate. This is more similar to the Cascadia subduction zone. And so we found in this section close to Colima, Jalisco, we found records of the aftershock that happened on 22nd June 1932 in Cuyutlán. The aftershock was 6.9 in magnitude. And this earthquake produced a large tsunami, and the tsunami was as high as 11 meters, the wave. And you can see the destruction produced by this tsunami and tsunami scour on these historical photographs. So we took the task also of modeling to prove if it was possible that an earthquake of such magnitude could produce this tsunami. And we found that no, I mean, the 6.9 magnitude earthquake couldn't produce such a large tsunami. So our hypothesis is that the earthquake triggered a submarine landslide. I'm not going to show you the whole thing, but just some of the results of the search for the tsunami deposits. And in this area, we found evidence of 2 units, one that correlates to the 22nd June 1932 event, and another event that happened in the 14th century. Further to the north, where the 1932 event occurred, the magnitude 8.2, that according to the descriptions, we interviewed people and we found a person that is still alive. I mean, and he was a child in 1932. And the description that they provide is that the tsunami went as far inland in one of the rivers as far as 8 kilometers. So we, there was a study by Comyn in 1933, and he also reported co-seismic subsidence on this area. And also he has some also reports of the tsunami. And so we found the evidence of this event in this site, in this region, La Saladita, but we also found evidence, the sediment record of another tsunami that happened approximately in 1900, and also the co-seismic deformation associated to this event, and another unit that dates back in 1563. So what we do in Mexico, there is a lot to do, but as long as there is an earthquake, we rush to the coast to do the post-tsunami survey and also post-earthquake survey. In 2012, there was a report of this big earthquake, magnitude 7.4 on the coast of closer to Oaxaca. And we did measure co-seismic uplift of this event. You can see these white patches are intertidal organisms that are dying because they are not covered anymore by the sea. And also there was, we measured the tsunami mass of the inundation at the time. And just last year, during the pandemic, and we had an event on the Oaxaca coast, magnitude 7.4. The earthquake happened during low tide. And that's one of the reasons why we saw a very small tsunami, but we record the co-seismic uplift, again, using the mortality of intertidal organisms in the region. So we have several questions and challenges on this region. And as I mentioned before, the Guerrero Gap is an area that we are studying. A group of colleagues also from UNAM are working on instrumentation offshore, but we are focused on using the paleoseismology and paleo-tsunami record to determine what happened in the past and if there is a possibility of an event happening here. And we also have the big question if it's possible to have a big rupture and not only the rupture of small patches as we know in using only the instrumental data. So the Mexican subduction zone is more than 1,000 kilometers long. So that question is still unanswered. And what we see also as questions that we need to solve is to find out what geologic evidence of historical recorded events we can find, and also prehistorical earthquakes we can find in the humid tropics. And I will tell you why it's difficult. And also, can we tell something about the source of large tsunamigenic earthquakes from the geologic record in these regions? One of the challenges of working in the humid tropics is the high temperatures and the rainfall, and also bioturbation, because what we see sometimes is scarcity of diatoms and foraminifera, and also these guys producing bioturbation, and access to sites can be challenging, as you can see here. So what we think is causing the poor preservation of microfossils in the humid tropics, first foraminifera that are formed of carbonates that are easily dissolved in more acidic water or more acidic environments. So that's one of the problems. And then diatoms, although they are made of silica, we found many broken pieces, and also diatoms that are deposited in saline environments. They can be more exposed to chemical and physical processes that will cause poor preservation. So one potential, but it's very expensive for us, is using DNA to find the record of these microfossils. And so what we are doing in the humid tropics is to use an approach, multi-proxy approach, using different tools. And the next one that we are trying to use is DNA to determine and to prove the procedence of tsunami deposits. And I'm just going to give you a brief tour of what we're doing now. And here in Guerrero, we are working in low marshes and lagoon marshes, augering, as everybody does, tough work, using also close to mangroves. It's been challenging work, but we have acquired through a donation from JICA, Japan, a geoslicer, and that's very helpful because normally the water table is really high. So this tool is very, very helpful. So we are doing a lot of field work and field descriptions of geoslices. And for modeling, we use, and to produce more detailed 3D models of the coast, we use LiDAR and we use also drones. And so some of the examples of here, And so we are in this process of analyzing all this data and coming to with some of the results. This is work in progress. We already proved that indeed there was a big earthquake and tsunami in 1787, and 3 probably large tsunamis on the Guerrero coast that now is a gap with no earthquakes, but if they happen in the past, there is no reason why they will happen in the future. And also, interesting enough, although we see with the instrumental data in more recent events cause seismic uplift, but in looking at the historical and prehistorical evidence, using geologic data, we find co-seismic subsidence preceding some of these tsunamis. And I mentioned already 3 tsunami earthquakes. Further work would be more ongoing radiocarbon dating. We have already more geoslices that record other events, and we are working on this. It's been also challenging using radiocarbon, so we are using OSL also as another dating method. We're thinking of offshore work to look and complete the record of tsunamis inland. Sometimes, as Pedro Costa mentioned, because of the anthropogenic influence, sometimes the deposits are not preserved. So we will attempt also offshore coring. And I want to emphasize the significance of the multi-proxy approach to future tsunami deposit research in these humid tropics. And finally, I think in Mexico that we have these records, well, they are longer in other countries like in India or in Japan, but at least in Mexico, we have records that predate the colonial time. And that's also very useful, combining this and using also modeling, as mentioned before. So offshore surveying and query is the next one. And I think I'm gonna stop here to give some time for questions.
Thank you, Professor, for your wonderful presentation. If you have any question, you can ask.
Hi, Maria. I have one question actually. So suppose in the coastline, so there is one tsunami during 1973, and then one tsunami, like one earthquake in 1973, and then one earthquake in 1978. But like both create suppose both create tsunami-genic sediments. So how you distinguish which one generate that deposit? Because like suppose you consider radiocarbon dating, so it is going to have some like plus minus 2 or like some year ranges. So how more accurately you can predict that, and which technique?
Okay, thank you. Thank you very much for the question. That's a really good question. We are not using radiocarbon dating for those events. We use, depends on exactly the year, but we are using lead 210 and cesium 132. So that's the approach for younger events. Because I know with radiocarbon, we couldn't, we have only, sometimes, you know, the plus minus could be 50 years or even more. So no, the approach that you need to use for younger events is lead 210 or cesium.
Okay, thank you.
You're welcome.
So like another just like kind of formal question, like I saw some photos from that Oaxaca earthquake recent 2000 during the pandemic one, because one of And Magda is work, like she just collects some field photos. So like that will be good area to work, because to know because this time they had like it had tsunami, so you can like work on that one, and then it will give you more, like if we do geoslicing and all those things, so maybe we can have more historical tsunami deposits in that area, I think.
Yeah, for the area of the 1787 event, you mean that? Or the Crucecita, you mean La Crucecita? Well, we're working on Oaxaca still. I mean, at the time we did all the research to find the evidence, we didn't have the geoslicer, but we have now a geoslicer. And so we probably use that to have more events and come with a closer, well, maybe with an approximate recurrence interval of events in that region. Yeah, something.
Yeah, thank you.
Good. Try to stop share.
Yeah, anyone else?
Yeah, we have one question from Asmita. So she's asking, like, OSL dating can provide good dates in tsunami studies, or?
What's the question, sorry?
Like she's asking, does the OSL dating can be used for tsunami deposits, tsunami studies, or something like that? Like, can we use OSL?
OSL, yeah, we did use OSL. We are using OSL. I did not. We just got OSL days for the Guerrero Gap, where I mentioned we found 3 different events. And the reason why is because the radiocarbon wasn't good. So we used OSL dating. We attempted OSL, and we are coming with better events. Yeah, I know there are some restrictions because in terms of using OSL, because the sun has to be exposed to light, enough time to light before it's buried. So so you can have an OSL date. But we were lucky, and we have good days for the using OSL. Luminescence dating is also really good. And another thing I want to mention, because, and I forgot, we found also, I think I mentioned that, archaeological sites. And for those, we have ceramics that we can also date, and we are dating them. So that's another approach we are using archaeomagnetics as a dating tool to give us an estimate of the age of the events.
Okay, anyone else? Dr. Mohammed, you have any question?
Yes, thank you very much, Maria. It was very interesting to hear your talk. I think there are very important issues which you have discussed. We are working, as a matter of fact, in Makran region in the Oman Sea area, and we are kind of recently initiated paleo-tsunami activities, which I'm glad to see that Brian F Atwater is also present in this presentation, and he's going to have a presentation. He is aware of that thing there. Of course, our aim was really to look mainly on onshore area for this purpose. Of course, that is much easier accessible, and then one can guess the things much more easier in that respect. You mentioned something about offshore, which is quite interesting. What do you think? I mean, is there any guideline you have? Is there any way that you can think of kind of getting better result? Are you thinking that we might have kind of the thicker sediment which could be deposited? Are we looking at turbidites? What are these things? If there are turbidites, all those kind of things, we might be able to get some result from seismic data, and this is something interesting. But of course, in this case, we have to look at very shallow, some sort of seismic reflection data to look at that, to see what we can get. But what about coring? I mean, is there anything, what kind of depth are we kind of looking at? I mean, I would appreciate if you can just, I'm sure there's a lot of open question. I mean, no, I think you cannot really answer all the question, but any kind of experience, any kind of advice you can say. Thank you.
Thank you, Mohammed. Yeah, we are attempting to use coring. The first approach was to perform more detailed bathymetry. We already published a paper with the interpretation of the submarine geomorphology of the region. And that was very important because I think the location is very important, the siting where we are going to be coring. In particular, in areas that we don't have a previous work done on this aspect. So first was selecting the sites, and we are selecting, and hopefully, I mean, we haven't been able because it's already like 2 years of pandemic, and we've been waiting for the approval to go offshore. And so what I'm expected to find, we did some coring previous to the pandemic in the region of Chiapas, because we had an event, but that was an intraplay event, magnitude 8.2, but it produced a small tsunami. And so we had the question if we could see a signature also coring. So we made some coring. We're still working on that. And what I'm expecting to do, I know not all in particular the Guerrero region, we don't have like these big canyons like in the Cascadia region where people has been working on turbidites. So we expect like finding the difference in the sedimentation rates, and see also a gap at different sediments. And in that, in terms of setting, we're working on the selecting sites on basins, you know, where we can have the position of sediments that might be transported by the tsunami, alloctonous to the site. And we will use DNA in this case to see an alloctonous signature for microfossils, another biological apart from the sediment from the sedimentological analysis. So that's what we use. So we are now for the Guerrero, we are just waiting with selecting sites. I think that's very important. We are not using seismic reflection data. I think we are gonna go straight to coring and collecting sediments.
Okay, thank you very much. Thank you.
You're welcome.
So next question is Aarti. Aarti, have any question? Hello, Aarti. You have any question? Hi
guys. That's Aarti from South Africa. Thanks, Maria, for your talk. Mine is just a very quick question about the foraminifera. As you just said that they are easily dissolved in more acidic water. Well, I'm also using forums and looking at forums to check my deposits of tsunami deposits along the South African coast. Well, I found that some of them, they are mostly corroded, fragmented. So how do you tell, is it there a way to tell that they have been corroded or fragmented due to the tsunami event, or is it just because of the acidic waters? Thanks.
So you're asking me about foraminifera, is that correct?
Yes, that's correct.
Okay, thank you. As I mentioned before, foraminifera has been challenging. If we find one or two, has been really lucky. I mean, 1 or 2. And so we have some work in progress. My postdoc that was working with us in Mexico, he found a way to, in the method, I mean, the tradition, he followed initially the traditional method for diatoms, and now he improved it, I think, because with the newest samples that we collected, we have over 1,000 and more diatoms, and that's very, very amazing. Something that we didn't have in the past. But with foraminifera, I was a little bit giving up because they are easily dissolved. If you think about the environments where we are working, the environments are very acidic, and they are, and then plus we have so much rain during the hurricane season that they are hardly preserved. They are easily dissolved. So I'm a little bit giving up on using foraminifera for that reason, because it's like looking for a needle in the middle of nowhere. So I couldn't answer more your question on that, because after the experience of looking for foraminifera in this region, we don't find much foraminifera. It's very, very seldom that we can see more than lucky 5 of them samples.
Okay, thanks a lot.
All right, so is there any another questions? One question is from Ahmed Amrish. He's asking the relationship between natural calamities and global climate change issues. Can you?
Climate and all this climate. Okay. Well, I think that's very very difficult to address, to respond. But I think the climate, in fact, Pedro Costa mentioned about one of the things that we should address in terms of climate change is sea level change, right? And that's something that that indeed we need to look at. But in terms of other kind of events, for instance, in Mexico, we have a phenomena called in Spanish, I don't know how to translate this in English, is mar de fondo, and that's when big waves are produced offshore, far offshore, and they come to the coast and float without hurricanes. This is not a storm. And but we've been lucky, I think, in the field, and we've been also observing this phenomena, and that's and this is climatic. I mean, this is not a tectonic event, and we can see how far the Mar de Fondo goes inland. Although it is almost like a storm event, like a big surge, but it never compares from what I've seen with a tsunami, the energy of the tsunami and how far inland the tsunami goes is not comparable to this Mar de Fondo. I don't know if somebody knows the name in English, but it's quite different. Also with the storm surges after hurricanes, we've been looking also after storms deposits to compare with the inundation that is produced by actually by a tsunami. And if the tsunami is large, it's gonna be not, I think my colleagues can correct me if I'm wrong, but I think it's not comparable. I mean, what I've seen in terms of the energy of a big tsunami and the geologic evidence of largest tsunamis in Mexico, like the 1932 and the 1787, I don't think we have ever seen a storm that goes as far inland as 4 kilometers or so. So this is something that we can use in terms to be reassured that we're actually really looking at that. And I'm not only looking at the tsunami deposit, I'm also interested in the earthquake that produced that. So I look also at the seismic evidence. So if I just don't look at the tsunami deposit and the sun, I try to understand what happened. If there was an earthquake, there must be a signature of a subsidence of uplift. And that's why we are analyzing also microfossils to tell us the environment that was before the event and after. So it's not only the tsunami, it's also the earthquake that we are that we want to answer as a question. As I mentioned, Pedro mentioned that we owe the people an answer. And we cannot tell them, oh, there was a tsunami only, but there was an earthquake and an estimate of how big was that earthquake. So I think that's very important. And sometimes we forget that there is also an earthquake signature. It's not only the tsunami. So the storm won't have any signature of an earthquake, right? So I think we have to go beyond only finding a tsunami deposit, but we need to address the question of if there was an earthquake too, and the signature of that event. I'm not sure if I answered your question, so hopefully I did answer.
Thank you, Professor. All right, so it's a great pleasure and honor for me to introduce one of the pioneer worker of paleo-tsunami research, Dr. Brian F Atwater. He is USGS geologist and an affiliated professor at University of Washington. He spent much of his career studying likelihood of large earthquakes and tsunamis in Pacific Northwest region of North America. In 2005, he published a book with others, The Orphan Tsunami of 1700, that summarized the evidence of megathrust earthquake in the Pacific Northwest on 26 January 1700. Known as 1700 Cascade earthquake, the earthquake produced a tsunami so large that contemporary reports in Japan noticed it. Today, he will talk about sediment deposition associated with tsunamis and storms with some examples. Professor, please share your presentation with us. Thank you.
Okay, thank you, Franco. Before I put slides on the screen, I'd just like to put them in the context of the comprehensive talks we've just heard. I'm going to try to pick up on just two of the themes that Pedro and María-Teresa have provided us, and they are both in this realm of distinguishing between different kinds of extreme waves. But one is the tectonic kind of trick, or that María-Teresa mentioned of using the land level changes along a coast as a guide to interpreting tsunami deposits and putting them in the broader context of apparent earthquake. And then the second is in serving the broader audience of people for whom we're in a way we're using earth science as the history of the earth as a natural tsunami warning system. And that comes with the challenges of that we all face of getting sort of our personal, almost our egos involved in the work. And it's easy to get involved in a way that that can almost bias one's own findings, because it's important for us to make significant contributions if we can. And the temptation is can be to overinterpret our evidence so as to come up with significant interpretations. So I'll give you a somewhat humorous conclusion on that point in a graphical form from a fine paper from 1961. Let me try to share the screen here. Okay, does this work for everybody?
Yeah.
Okay, good.
Fine.
All right, so I'm wearing a Chilean gorro, but because it's winter here in Seattle, and the room I'm working is cold from home. In our context here, this is for my first example on the tectonic, the tectonic shortcut, in a way, of distinguishing between tsunami and storm, is that if one is close to a fault that produces land level changes, that in turn the seafloor part of that is the driver for the tsunami. So if your coast expresses those land level changes, then that becomes a shortcut on distinguishing between tsunami and storm. And you can think, for instance, in Mohammed's case, with the Macron, that it would be important for the paleo-tsunami work there to try to deal with land level changes if they're in the offing along the Macron coast. So in our case, the subduction zone here was, I guess it was first recognized soon after the plate tectonics revolution in the 70s. And it was in the early very late 70s and early 1980s that geophysicists started to wonder whether you can get very big earthquakes here. And the work was pushed forward by the Nuclear Regulatory Commission because of some Fukushima vintage plants that were designed at the time the Fukushima plants that were about to be installed on the Washington coast. And the Nuclear Regulatory Commission was worried about the evolving science of the subduction zone. So it was in that broader context that geologists stepped in and extended Earth history farther back than the 200 years of written record here, or the seismological record that's shorter, to look back centuries or thousands of years. And shallow faults across Puget Sound ultimately came to light that also had their own tsunami history. So everybody knows this, but it's just terribly useful for this little tectonic trick, right? That what drives the tsunami with uplift over the fault rupture, essentially, and subsidence in the areas where the overriding plate is stretched during the earthquake, that those land level changes can show up in tsunami records. And for us, there are these conifers that go for a swim after the land drops, and centuries later, you can have these geological records in form of a sort of ghost forest and the deposits on top. And so at this Washington example, this goes back, let's see, there are two root horizons, I think, that you can see in the picture. One's very close to the water level, and then the other is where the person is standing. And so these represent former forests that got dropped down. And since the last one dropped down in 1700, where the person's standing, the land has been rebuilt by tides, but trees have yet to return to this landscape. It hasn't been freshened up enough. but these provide the geological evidence for cycles of ups and downs that give clues to subduction earthquakes. And so in that same picture, there was a shovel handle and the next to the person, and there's the same shovel here, and you can see a little bit of sand that's a couple of layers of sand with some mud in between that coat the forest floor, and one of the spruce roots in growth position. So from this, if instead you're dropping down a tidal marsh in this picture, you have this association then between land level change and tsunami. And if you're working in a place that's remote enough from the sea or from big rivers, where it's very difficult to get a sand deposit by any other means, and the only sand that you see is right there at the stratigraphic marker of abrupt land level change, then that becomes a way of by coincidence. It's just an argument of coincidence. It doesn't tell you anything about the process of sediment transport, but it does tell you about the mechanism, the cause of the surge of water that deposited the sand. It implicates the same phenomenon that produced the land level change. So that's the argument by coincidence that María-Teresa was using in her Mexican examples. A broader public here, to middle school teachers who have painted an outcrop with, first they've tacked nylon window screen and then used a water-loving glue it's a non-toxic thing. It looks like a mess. And you peel it off and you can see the buried soil of a salt marsh that's from 1700, and then multiple layers of sand that probably represent the individual waves in a tsunami wave train in the evening of the 26th of January, 1700 by the Japanese dating. So this, but you see the paleoecological context writ large here. The gray mud above those sand layers, though the oxidation is working down into it, is the evidence for land level change there. And in some cases, you can get people into the picture. María-Teresa mentioned examples with I think also Pedro did, with archaeological sites. And the example I'll give you here was an elk. There are these deer-like animals, big ones, elk, and this was an elk processing facility in the state on the Oregon coast that got dropped down and covered up with a sand sheet. The fire pits were dug into sand dunes. And then after the first thing that the fire pits saw after the down drop was the tsunami with the sand sheet there. And then that's been mapped very, very carefully at this estuary by Wendy Grant and some others, and tidal marsh deposits above that, confirming that you've had a land level change where you've put a elk processing facility on high ground of dunes. You've put it out of business in the long term by the tides that came in afterwards. The same things that it's the tides that kill the trees, right? Not the tsunami. Okay, so that's our first example. The second example that deals more with the psychological challenge is a tsunami versus storm story from the Northeast Caribbean, and the place we're going to is Anegada. And María-Teresa, correct me, but I could say that I'm swamped with overwhelmed or swamped or inundated with information, and I could say estoy anegado. Is that right? And so So it was a term Columbus applied to this, or his crew applied to a low-lying island that looked wet to them. And it adjoins the Puerto Rico Trench, which it kind of brings to mind Cascadia of the 1980s or something like that, where it was completely open question as to whether very big earthquakes happen there. And the question of the earthquake and tsunami potential along the Puerto Rico Trench is still very much an open one. There's a setting of Anegada on some nice bathymetry, and you can see out on the outer rise, on the outer wall of the trench, these big scarps that are thought to be from normal faulting, and that rather than thrust faulting may be the prime candidate in terms of making big tsunamis in this part of the world. That the plate motions along the Puerto Rico Trench are practically pure strike slip. This is a low-lying place. The highest ground is about 8 meters, and it's Pleistocene coral reef deposits that make up the high ground. And then you can see the Holocene beach ridge plains off to the left, salt ponds out in the middle, a fringing reef on the north side that drops straight off into the deep water of the Puerto Rico Trench, essentially. So it's a very efficient way for a tsunami coming from the Puerto Rico Trench to come up onto this island, nothing to break. Well, there's been quite a bit of work by a diverse cast. Some of the principals include Michaela Spiske, who's now has just a brand new publication about Hurricane Irma in 2015 or something, and its effects on this particular island. But there are these historical hurricanes that have managed to stir up the salt ponds and produce washover fans that extend tens of meters inland along the shore, but very little else. There's sometime between 1650 and 1800 on this island. There was a bigger surge of water that managed to stir up the mollusks of a marine embayment that was there at the time in the position of today's salt ponds. And that made quite an impressive deposit, but it didn't move coral colonies from the fringing reef. But in the last centuries before Columbus, there was an event that did move those coral, broadcast them inland quite a ways. And the question there is whether that was a tsunami or a storm. The 1650 to 1800 has a known possible source with Lisbon as a transatlantic source. So very briefly, the evidence, this before Irma, but the Irma of Category 5 had similar effects. And I mentioned small fans and the stirring up of salt pond bottoms. There are storm surge limits from human observations on the south shore there. And then there's a lovely coral rubble ridge that got displaced inland a bit during Hurricane Irma. They read about it in Michaela's new paper. There's Michaela in the foreground and this rubble ridge to give you an idea. And she ascribes this to storm effects. The possible Lisbon example is the distribution of deposits that have been mapped that are probably represent this particular flood from the north. And then finally, as for the choral class, the main actor is the main what do I want to say? It's the photogenic one for sure, is brain coral, and plotted here are, let's see, I think it's just the red ones are just brain coral, and then there are quite a few limestone boulder fields, and then sand sheet, and all of this managed to go up onto high ground in ways that neither the historical hurricanes nor the this event between 1650 and 1800 managed to do. Here's one of those coral heads inland, some hundreds of meters out on on the fringes of one of the salt ponds. And another example. Whoops. So yeah, the dating with these, you let's see, what have we plotted here? So this is just in radiocarbon years, because converting from radiocarbon time to real time in this particular area is difficult because of uncertainties in the marine reservoir correction. But it's easy to compare the ages, the raw radiocarbon ages, with one another to ask whether you might be looking at a single event or multiple events. And this group of ages on coral boulders is most simply explained by a single event with some old dead coral being brought in from later. There's some problems with actually with meteoric water contaminating the samples in the young direction, but by and large it's a coherent set. But I guess for a bit we were, those of us working on this were confident that we were dealing with a tsunami in this case, but this was before 2013 super typhoon Haiyan. And at this place, Hernani, there were, I think Pedro put up the term infragravity waves. I can't explain them, I'm sure he can, but anyways, it's a surf beat is another term that's been applied to it. And this was a setting that looked very much like the North Shore of Anegada, where there were waves, there were waves, storm waves of different, coming in little bunches that would be of different sizes. And some of the big ones would pile up, I guess, against the reef, and then that would give you a surge of water going across the flat between the reef and the shore. And the video taken from this town Hernani, it looks just like a tsunami. And so it really gave us pause for thought as to whether that kind of thing is possible at Anegada. And we still haven't been able to rule that possibility out. So it's likely a tsunami, but there is a possibility of a storm explanation. Andrew Kennedy is among the people who've worked with the large class that the super typhoon was able to move. I suppose this becomes also a connection with global warming connection there between that and the kind of geology we do. Well, the psychological challenge that I alluded to at the start was crystallized by a student of the, I think, of the Proterozoic and early Paleozoic. He was interested in this. Look at the date on this, 1961. This is before plate tectonics, and he's dealing with paleobiogeography without the without the present day reconstructions of Gondwana and stuff like that, right? He's trying to figure this stuff out. And so in a review of that, he gets worried a bit about having so many uncertainties and how confidently he should state his assertions. And this for us because of the interface with people who care about the results, right? People worried about these natural hazards, and sometimes geology comes up with information that's available by no other means, and we have to state the conclusions in some nuanced fashion that it's like communicating global warming, right? So anyways, here's Preston Cloud's graph, and he explains it this way. So you can see how in this little these sentences, he explains the shape of that curve, right? And this pertains, I think, also to some aspects of tsunami geology that it can get, the interpretations can get rather indirect, and these open up the opportunities for us to stray from Preston Cloud's scholarly ideal. So I'm not sure where to put the Anegada work on this graph, but in any case, I think some people would say that we are, if you push it in the case of Anegada, the storm alternative, that you're working in the lower right part of this graph, and that you've deviated from the scholarly ideal in that direction. But anyways, those are two examples, tsunami versus storm, in one case using the tectonic setting to help to rule out storm as a likely explanation for sand sheets in a simple way. And in this case, where it's not been possible so far to use that tectonic explanation, and suppose, for instance, we're dealing with an outer rise tsunami source, we're never going to see at Anegada land level changes from an outer rise earthquake. And so we're going to have to be dealing with the usual situation of distinguishing between tsunami and storm without that tectonic crutch. Okay, thank you.
Thank you very much, Professor. Anyone have questions? Yes, Professor Costa have one question.
It's more a comment, and first let me say thanks to Brian to this really nice presentation. And also to address one of the earlier questions that was made. If we think about climate change, and if we look at the models, especially in mid-latitude areas, we are expecting an intensification of storm events. Not only they will be more frequent, but especially they will be more intense. And one of the aspects that I would like to hear your opinion on this is that, and I'm going to refer to some experience that I had on the Hercules storm in 2014. So the fact that we had 3 successive events in that month of January and early February 2014 made the signature be totally different. Namely, in terms of boulders, we were monitoring the boulders, and we saw that the boulders moved after the Hercules, and then I think it was, I can't remember, Cynthia or Nadia, I can't remember the name. 3 successive storms that moved the boulders in a successive way. On the other hand, on the sandy deposits, everything was basically eroded, because the system had not time to recover. Coastal system had not time to recover. So I was wondering, and this is pure speculation, and also to address some of the earlier questions, I think it was from Professor Mohammed. Are we going to see a shift in the type of signature on these events, especially because of their recurrence? And if the balance in the coastal system is so disturbed, I think I'm afraid that we will, the type of signature that you're seeing in Anegada is biased to the extreme most, I would say, because it's an area where you have other events. So I'm wondering if in the future we will have more problems than we have even more this tendency to the extreme most because systems will not be able to recover, or if we have a different type of cumulative signature because of being a succession of events. And this is just pure speculation, but to hear your opinion on that.
I'm not quite sure I get it yet. On the one hand, if you could say that that we North Americans who've contributed an outsized share of CO2 have made tsunami and storm geology easier because the more intense storms happening more frequently will allow us to get a very good statistical sample across the spectrum of those. I'm being facetious, right? I'm not very happy with the situation, but that's one view. But what you're talking about is clearing out the system somehow so that then you bias in a different direction. I haven't thought enough about that. But boy, you know, there are they're very good, these wonderful storm move boulder studies, right, in Ireland and so on. And there's a group started up now by Andrew and Rona Cox and others on this. And so it's a wonderful counterweight to the tsunami geology that was using boulders and people saying, well, you can't possibly move this by storm, therefore it has to be tsunami. And the storm boulder people have come up with alternatives that way, right?
Yeah, Mohammed, Dr.
Yes,
Mohammed.
thank you very much, Brian. It was wonderful to hear you. And I think the presentations, as usual, excellent. It's, of course, there are lots of topics. As I mentioned just before, we're quite young in that respect in Macron region. And any type of result and experience can really help us. And especially at the West Macron, we have not true evidence as yet to show we had a tsunami. But I mean, I personally believe we did have it, and we will going to have it. But of course, we are trying now to use this case. That boulder discussion, I think, is very, very interesting in that respect. That probably another alternative that we have seen the pictures that we have taken. Probably these are the one could help us somehow to get into that. I was wondering if you can agree with me about the boulders or sedimentations when we want to distinguish between storm and Apollo tsunami. We think about distances from shore. I mean, sometimes the storms could not, I'm assuming, could not really take large boulders or large amount of sediments into the area which we find. Therefore, I think the thickness of the layers might be an indication of, okay, distinguishing between storm and tsunami. Is that feasible? Is that something which one can look at it and go through? Of course, we have lots of kind of climate case as well, which could also help us, but I'm not sure how far back we can go with climate. Thank you.
I think, as Pedro said, Mohammed, it's so much of this is local. If the Philippine analog I spoke of that may apply to Anegada, where you ended up with a tsunami-like surge that did move class far inland in the Philippines, that situation, I think it hinged on having a fringing reef and a shallow water area behind that to set off these kinds of surges, and maybe you would not get that on the Macron coast, for instance. But yeah, for distances, you can turn to to some of these modern storm boulder studies that have documented how far inland they go, and those are going to be tricky. You take a cliff top in the North Sea and you try to compare it with a cliff top at Chabahar, right? But since you're familiar with both areas, you'll be able to figure this out.
Thank you.
Anyone else want to ask question? Luis, do you want to ask any questions?
Yes, hello.
Hi.
I don't know if you hear me.
Yeah, perfect. Go ahead.
Yes, okay, thank you. I'm in the public transport, so it's not so easy. But yes, I was just wondering, so thank you for the talk. It was like very, very interesting. And I was wondering if there are other big boulders in the Philippines that could testify from much older events than the super typhoon of Hainan. And if those boulders can erodate very fast, how far in times can we go thanks to those objects? So yeah, thank you.
Soon to be Dr. Cordery. So
yes, thank you.
She defends on Monday, and I get to sit in on the defense, and it's a very intimidating thing because the French word I guess it's French word they use, we would say a defense committee, right? But they use the legal term jury, so I imagine a criminal trial, but it's not going to be that way with Louise's defense. Anyways, she's got a marvelous dissertation that but I don't remember the details, Louise, but I believe is it a German investigator? Is the family name? And there was some attention with that field work in the Philippines, but maybe there's somebody else in this group who has experience there who recalls it better. But yeah, it'd be worth looking through those Haiyan papers for evidence for prior boulder transport.
Okay, thank you very much.
Yeah, next question is Robiline. Robiline, can you explain your question? Hello? Yeah, she's asking, I'm also working on the Eastern Philippines, and it is difficult to determine whether the boulders are moved by the tsunamis or storm surge. Are there any distribution pattern of boulders that can be related to tsunami or storm surge movement?
I like the further comment on the chat. I'm sorry I cannot unmute since it's already past midnight. Thank you for staying up. So I have zero experience with this, but I guess if I were trying to sort this out in the Philippines, and what you actually, that area faces a trench. Does it face it? It joins the plate boundary, I think. So anyways, so you would have that ambiguity, but the leg up that you have is the deposits from Haiyan, right? So at least those provide the modern analog. What are other examples where people have done this? On this in India with the 2004 tsunami in Tamil Nadu, Srini Vasalu went out and looked, and there was also a cyclone, right? And so there was a head-to-head comparison there between the two. So working with again, going back to Pedro's points, that so much of this is local, and that the context matters, that the person trying to sort this out has to fall in love with the entirety of the coastal geology, and then extract from that coastal geology the information you want, but first having understood the bigger picture, and that the modern analogs really enrich that.
Yeah, Professor, thank you. Any questions from anyone? I think there is no more questions. Yeah. So thank you very much, Professor, for your wonderful presentation. And I will discuss about Namilink projects with you in very brief. This is the project. It's an initiative of Coastal and Marine Process Commission, INCOA, mainly led by early career researchers working in paleo tsunamis. The aim of the project is to developing network among researchers working in paleo tsunami, and to develop an online data repository of tsunamis, storms, and other coastal sedimentary deposits, and identify the potential areas for future tsunami research, and developing different projects by using these collaborations. So in our activity in 2022 focused, basically we'll develop an online data repository for coastal sedimentary deposits. So we can come together and we can share our field photographs with us, and we'll save the data in that cloud. That data may be related to deposits and sedimentological parameters, lateral long, and all kind of stuff, whatever you want to contribute. And we will organize those data in a proper way and listed them and classified them in a cloud reservoir for future research and development. So whoever contributing to the cloud database, we will give access to them for their research and development work. So what I'm thinking that if once the data is collected, we will develop a project in a Google Earth where we can showcase the deposits across the globe. And once we have that, we can easily get the different characteristics of the deposits across the world, so that in future we can able to write some papers or some projects that will be useful. So in 2022, we are also planning for a workshop that will be a physical workshop to study the modern techniques to decipher the coastal sedimentary deposits. So we are planning to conduct this in France with Dr. Rafael Paris Laboratory of Magmas and Volcanics. So in which we get we are suggesting that we will organize a workshop, 1 or 2 day workshop, in that we will learn the techniques, particularly CT scanning, X-ray related stuffs from Rafael Paris, and we can enhance our technical skills by using these opportunities. So once this collaboration was done, we will develop different projects based on this activity. We will apply for different projects across the world. So I'm not very much aware of that, but I know very little information. You can come up with your ideas, and we will sit together with a group of scientists, technologists, and computer-based specialists, or somebody is working in artificial intelligence and machine learning technologies. So if we gather such a group to model this geological data and to develop meaningful projects in this duration, that will be the long-term goal of this project. So this is our team. I'm just leading the team. I'm just working as an innovator at Startup Incubation and Innovation Center, IIT Kanpur. I'm specialized in paleo-tsunami. Similarly, Professor Beverly Goodman is there. She's from Israel, Haifa University. She's a marine geoarchaeologist, especially working in tsunami deposits and submarine paleo-tsunami deposits. Rafael Paris also there. Is specialized in X-ray tomography in paleo-tsunami studies, and is from France. And we have Isabel Hong from Simpson Fraser University, Canada, and she's working in paleo-tsunami. From India, we have Anand Shabari Karthikeyan. He's in NIOT right now. He's also specialized in paleo-tsunami. And Dr. Sambit Prasanjit Naik, he's working in Pukyong National University, Korea. So he's a specialist in active fault. And Dr. Shanti Sarup Sahu, assistant professor working in Utkal University, India, is specialized in active fault. And Dr. Smita Mohandi, she is also working in active faults and presently working in NIAS IASC campus, Bangalore, India. And Shreya Arora, she is right now she's in US, Bates College, US. And Dr. Ghulam Rasul Bhatt, he's also working in active fault. He's presently working in the Government College, Jammu, India. And Gurvinder Singh, he's working in IIT Kanpur, is specialized in active faults. So we are looking more early career researchers or more experts in group, especially working in paleo-tsunamis and coastal research in future, so that we can build a good team that comprised of different flavors, means some people working in paleo-tsunamis and the sea level changes, especially some people working in modeling, some computer-based professionals having some good mathematical skills, so that we can develop a good team and good projects so that we can move ahead with this project. So I am requesting your support for this project, and looking forward to seeing you all in this group. Thank you very much. So our next presentation from Isabel Hong. She's an SF at Science postdoctoral fellow at Simon Fraser University, Canada. Isabel is interested in understanding the short and long-term effects of relative sea level changes caused by geohazards in coastal environments. She used sedimentary and microfossil diatom analysis and statistical modeling to reconstruct the paleo environment over millennium timescale. On behalf of INCOA Namilinks team, we are inviting Professor Dr. Hong to present the presentation. Thank you.
Thank you, Franco. I think you have to stop sharing so I can share my screen.
Yeah, sure.
Great. Good day, everyone. I am having currently some internet issues, so please let me know if you cannot hear me, and I can turn off my video and hopefully provide all of you with a smoother presentation. So good day, everyone, and I look forward to sharing with all of you some paleo-tsunami research that I was fortunate enough to conduct in South Central Chile, along with my co-authors. And we're fortunate enough to publish this research in the Holocene, but I would like to begin by talking about how my study area fits into paleo-tsunami research and why there's interest in studying the history of tsunamis in South Central Chile. So broadly speaking, this study area is located along the Chilean subduction zone, where we have the subduction of the Nazca Plate underneath the South American Plate. This South Central region, as shown here in box B, shows a 500-year historical pattern of tsunamis generated by subduction zone earthquakes originating from both the north, as shown in red, and the south, as shown in dark yellow. So here we have time on the x-axis here on this figure, where we have present day shown on the right and previous subduction zone earthquakes and their rupture lengths shown on the y-axis. Earthquakes shown in dashed lines are rupture lengths that are inferred from historical observations, and earthquakes shown in the solid lines are rupture lengths that were measured by instrumental observations. The 2010 earthquake caused rupture that overlapped with the northern extent of the rupture during the 1960 Valdivia earthquake. So I'll focus your attention on the town of Quirico, which is shown here in the middle and labeled in bold. Quirico is uniquely situated as a site of rupture overlap between this northern rupturing 2010 earthquake and the southern rupturing 1960 earthquake. So the motivation of the study was that due to the location of Quirico as a site of rupture overlap, can we find a record of older tsunami deposits from both the northern and southern rupturing subduction zone earthquakes? Quirico is a small fishing town located at the mouth of the Quirico River, where the river is shown in blue. The floodplain highlighted in green has abandoned meanders shown here with these arrows that formed when new channels cut off the bend. So it's causing aggradation of alluvium in this abandoned meander. Now, following the cutoff, the aggradation of PD sediment in standing water created a wetland environment ideal for the preservation of coastal sediments, such as tsunami sands. So we set out to investigate riverbank exposures and an abandoned meander in the lower Quirico River Valley here for stratigraphic evidence of deposits from past tsunamis. Now, eyewitness accounts describe the 2010 tsunami as having inundated the floodplain of the Quirico River, but was confined to the river channel farther upstream. Initial tracing of the 2010 tsunami sand bed found thicknesses that range from 2 to 5 centimeters thick along the riverbank. thinned out to patchy deposits of about 1 to 2 centimeters in thickness in the abandoned meander. So this study was focused on the lower 1.5 kilometers of the floodplain, which we will focus on in more detail. Following previous paleo-tsunami investigations and studies aimed at learning more about the inundation extent, earthquake source, and recurrence interval of historic and prehistoric earthquakes, we set out to investigate Quirico for stratigraphic evidence of deposits from past tsunamis. To do this, we used a combination of hand-dug pits, gouge cores, and riverbank exposures to describe the sedimentologic and stratigraphic characteristics of the sand beds in sequences of PD sediment in the abandoned meander and stratigraphic sequences of muddy fluvial sediment along the riverbank. We collected blocks of sediment from a representative coring location for additional grain size measurements, as well as microfossil diatom analysis to determine whether or not there was evidence for the sands having a marine source. Additionally, we also conducted cesium-137 dating and radiocarbon dating of plant macrofossils in the organic rich units to obtain the ages of those stratigraphic units. And then to estimate the timing of tsunami deposition, I applied an age depth model using OxCal. So fieldwork was conducted in February of 2013. Stratigraphic units were described and correlated along 2 transects in the abandoned meander, an X to X prime shown in red and a Y to Y prime shown in yellow, as well as a riverbank transect, the Z to Z prime shown in blue, that followed the riverbank exposures upstream. Then the relative elevations of these cores, pits, and riverbank exposures were measured using a total station. And then these elevations were tied to a tidal datum measured with a temporary tide gauge that we installed on the footbridge as shown in the photo in the upper right. To determine the elevation of the tide gauge relative to local mean sea level, we matched our tide gauge observations with the tidal predictions. So I'll move on to talking about these criteria. So using previous tsunamis, studies outlining criteria for tsunami deposits, and also using the 2010 tsunami sandbed to guide our interpretations of older deposits, our evidence for deposition by tsunamis that inundated the floodplain include these 5 criteria. So the first criteria is erosive basal contact overlain by sand. The second criteria is that the sand units had to be landward thinning. The third criteria is that the sand units were widespread. The fourth criteria is that the sand units were upward defining. And the fifth criteria was that there would be independent measurements using other proxies such as microfossils to indicate that there was a shoreward signal or marine or mixed signal of the tsunami sand beds. So we'll talk about the results and talk about how these results fit into those criteria that I just established. So we interpret sands that have a sharp, and by sharp I mean less than 1 to 3 millimeter lower contact with the underlying silty peat or sandy silt unit as indicative of a rapid change in sediment source. We found a total of 6 sand beds, where 5 of those sand beds had sharp and erosive lower contacts. The 6th sand was the lowest sand stratigraphically, and it constituted the basal unit of most of our coring locations. So because we couldn't really determine whether or not it had an erosive lower contact, we do not include sand 6 as a candidate tsunami sand bed. The second criteria, that the sand units are landward thinning. So the deceleration of tsunami flows can lead to landward thinning of the tsunami sands. So we trace the landward extent of these sand beds along the riverbank exposure with the Z to Z prime transect. Results of our stratigraphic mapping upstream are shown here in the figure in the upper left, with horizontal at sands 1 through 5 are widespread and draped over the pre-existing topography at Quirico. As mentioned previously, sand 1, the 2010 tsunami sandbed, we found thicknesses that range from 2 to 5 centimeters along the riverbank and thinned out to patchy deposits ranging from 1 to 2 centimeters along this abandoned meander. I'll focus on the stratigraphic mapping of the abandoned meander to show the widespread nature of the sandbeds that we found. Sands 2 through 5 extend continuously up to 100 meters in the abandoned meander. Although the sandbeds were not found in every core or pit, these tsunami deposits can be discontinuous and patchy due to the variabilities in tsunami flow, sediment source, sediment concentrations, as well as the irregular topography upon which the sandbeds were deposited. But because pit 13 here shown with the blue arrows did include sands 2 through 5, as well as this basal sand 6, we collected samples from this location for additional laboratory analysis. So I'll talk about criteria for next, that the sand units are upward fining. Grain size analysis was conducted at about 1 centimeter intervals near the lithologic contacts, and then roughly 3 centimeters in the homogeneous sediment from pit 13. Results of the grain size analysis are shown on the right of the slide. So on the left side of the figure, we have a stratigraphic column showing the units found in pit 13 with the sand beds shown in yellow. Adjacent to the column are grain size results shown as the relative volume of sediments sorted by grain size in phi on the x-axis, with warmer colors indicating more volume compared to cooler colors. Adjacent to that is a grain size distribution plot of the fine fraction, that is this D10 value throughout the core. And results of fine fraction measurements show that sandbeds are coarser than the interbedded freshwater peat that we observed in the field, and that sands 3 and 5 displayed these upward fining characteristics. Additionally, we use diatom analysis to aid in our interpretation of sediment provenance, specifically looking for diatom species with marine and brackish salinity preferences within the tsunami deposits, suggesting a marine signal for the sandbeds. So samples were taken for diatom analysis at about 1 centimeter intervals near the lithologic contacts to up to 15 centimeters within the homogeneous sediment. Diatoms were then identified to species level and classified based on their salinity preferences. Sands 2 and 5 show an increase of about 15 to 35% in marine diatoms as opposed to the silty peat units below. Additionally, although sands 3 and 4 show a mixture of freshwater, brackish, and marine diatoms, we do observe that that type of mixture can also be indicative of more shoreward signals and shoreward sediment provenance. And additionally, that sand 3 showed the presence of anomalously marine diatom species, such as Delphinae cerulea. And so we interpret the upper 5 sand beds that we found and traced along the lower Quirico River Valley to have been deposited by tsunamis. Although sand bed 3 was the only sand bed that met all of our criteria, we interpret beds that displayed multiple criteria as probable tsunami deposits. We found also that the stratigraphy of the abandoned meander shows that it's a relatively good depositional environment that preserved tsunami sandbeds well. And additionally, that the organic matter that accumulated in the wetland environment provided by the abandoned meander also provided us abundant material for radiocarbon dating. And so what we found then, trying to put together the timing of these tsunami sandbeds, is that we conducted interviews with residents of Quirico to confirm that that superficial sandbed 1 was deposited by the 2010 tsunami. To confirm that sandbed 2 was deposited by the 1960 tsunami, we collected sediments from above, within, and below sandbed 2 for cesium-137 analysis, as shown by the boxes in the stratigraphic figure. Because cesium-137 was introduced into the atmosphere after 1950 as a product of above ground nuclear testing, presence of 137 cesium above and within sandbed 2, but not below it, as shown with the white boxes indicating absence and the black boxes indicating presence. It constrains the deposition of sandbed 2 to after 1950. Next, the triangles in the stratigraphic columns show where plant macrofossils were selected for radiocarbon dating. The plant macrofossil material was then sent off for AMS radiocarbon dating and subsequently calibrated. And then these ages were put into OxCal to estimate the timing of tsunami deposition. And so our analysis of the historical records show that large tsunamis generated by great earthquakes from both north and south of Quirico are likely candidates for sources of the Quirico tsunami deposits. Our interpretations rely on matching the stratigraphy at Quirico with historical records. Now, based on eyewitness accounts and confirmed by results for cesium-137 dating, we can confirm that sandbed 1 was deposited by the 2010 tsunami and that sandbed 2 was deposited by the 1960 tsunami. Our age model results suggest then that sand 3 was deposited between 1820 and 1959, and sandbed 4 was deposited between 1690 and 1910. During this time range, there are historical accounts of 4 tsunamis that could have inundated Quirico: 1730, 1751, 1835, and 1837. Based on historical and geological evidence, the earthquake in 1837 ruptured south of Quirico, and only a low tsunami was recorded at the northern end of rupture near Concepcion. In contrast, the 1835 earthquake likely ruptured between Santiago and Tirua, generating a higher tsunami. So we suggested sand 3, which forms a prominent widespread deposit at Quirico, was deposited by the 1835 tsunami. If so, then sand 4 could have been deposited by either the 1751 or 1730 tsunamis. Now, descriptions of the 1751 tsunami suggests that the earthquake began in a similar location to the 2010 earthquake rupture between Santiago and Tirua. Destruction, though, of the 1751 tsunami prompted inhabitants of Concepcion to move the city inland. In contrast, the 1730 tsunami was generated by an earthquake that likely ruptured between La Serena and a point north of Concepcion. So although the 1730 tsunami could have reached Quirico, it is unlikely that a deposit from 1730 would be as thick and as extensive as those produced by a tsunami generated by 2 other very large and closer ruptures during this time period of 1751 and 1835. So we suggest that sand 4 was deposited by the 1751 tsunami. And finally, our age model shows that sand 5 was deposited likely between 1445 and 1490. It precedes the existing historical earthquake catalog for South Central Chile and represents a prehistoric tsunami that extends the record in this region by about a century. And so in summary, we found 5 tsunami deposits at Quirico from the modern and historical record, with an additional prehistoric deposit dated between 1445 and 1490. Stratigraphic investigations along the abandoned meander and along riverbank exposures show that abandoned meanders can be a good depositional environment for tsunami sandbed preservation. And finally, that the records we found at Quirico support an average occurrence rate of large earthquakes and tsunamis of approximately every century. And with that, I would like to thank you all for your attention.
Thank you, Isabel, for your wonderful presentation. And if any questions, please ask. Any questions? Yes, Professor Brian.
Hi, Isabel. Thank you very much for your talk. And I guess maybe three questions here, if I may. One is on this matter on sharp contact versus erosional contact. What was the evidence that you saw that material had actually been removed from the surface of on which the sand sheets were laid down? One can imagine that in that environment that you're dealing with decelerating flows, and sand grains might be just gravity is making the sand grains fall onto the bed, and at some point it's just going to be raining out of suspension almost, and you could get a sharp contact without it being erosional. So I wonder whether how widespread the evidence for erosion was. Let me just throw in one more question, or two more, that you can keep as well. What on the matter of upward fining? Usually you're dealing with tsunami wave trains, and the first wave is not necessarily the biggest one. So upward fining, if you had the second or third wave be the largest, and yet you had deposits from waves number 1 and 2, you could get a different sequence. I think you've seen that probably at the Neowayakam River, Willapa Bay, that down near the river mouth, that the basal deposit is not the coarsest. And then finally, I wonder what you might say about the completeness of the record that you have. A notable earthquake that's not represented in the time sequence you showed us is 1575. And there's quite a bit of historical evidence just to the south of the enormity of the tsunami from that. So if 1575 is really absent, is this an example then of the unavoidable imperfections of geological records, and sort of a cautionary tale on completeness of record? So those are three questions: erosional base, upward fining, and completeness of record.
Yeah, thanks, Brian, for your questions. I'll maybe answer them in reverse order. So as far as completeness of the record is concerned, I think that's possibly a legitimate point to make about Quirico, because there's a study published in Tirua that's not very far away from Quirico, but just north of Quirico, that does show evidence of preservation from 1575, but it's not here at Quirico, and that may be potentially an issue of maybe more extensive coring that I could have done to maybe look for evidence of it. But that said, the record at PID 13 that is believed to be as continuous as possible as we could have found in our depositional environment, it just wasn't there. Mm-hmm. So to speak to that record of completeness versus incompleteness, I'm not sure really what it could have been about the environment at Quirico, that maybe the tsunami had inundated there, but there just wasn't very good preservation of evidence of this. I'm just not sure. Unfortunately, I can't really speak too confidently on that aspect, but I think that is something to consider. And then your question about erosivity. So we did use 2010 as somewhat of a modern analog for guiding our interpretations. And although there wasn't, as you mentioned, there wasn't a lot of strong evidence for erosivity at Quirico itself, but in other locations like Tirua, we could find some more evidence of, like plant material being sort of pushed down and sand deposits being deposited on top of that from the 2010 tsunami. There was also, interestingly, to speak to your effort, to your second question about pulses and sort of generating this issue of finding upward. There were evidence of anthropogenic materials, so candy wrappers and things like that being included within the 2010 tsunami itself, as well as 1960. And so I do agree that because it wasn't strong evidence for erosive contacts, but we do have sharp lower contacts, and that's definitely the criteria that I held on to the most. And certainly to then speak to your second question about this finding upward sequence not necessarily being indicative or the only criteria we should rely on for tsunami deposits, I definitely agree, because we didn't see very strong evidence of that. We only saw it in 2 of our 5 sand beds, and even that, it wasn't quite as conclusive and as strong as I had wished it to be. So I think, again, Brian, you bring up a really good point, and to Maria-Teresa's point about relying on multiple proxies and really having multiple lines of evidence to show that we have probable tsunami deposits is the best way to go about this.
Okay, next question is from Professor Maria-Teresa.
Thank you very much for your talk. I read your paper, and congratulations, Isabel. It's a really nice work you have done in Chile. And so just looking at your work on meanders, I was also thinking on the questions that Brian posed, but I have another question related to the, I understand in Chile the tides and the difference between tides is really high. Like it could be, I don't know locally in your region, but it could be as high as the tide. The difference in tides is close to 7 meters. That's correct. And then I wonder if the signature of apart from the when you have like floods from river floods, and then you have a high tide, how far is the influence of marine water entering the river? Because I've seen it in some areas that how the tide goes into the river really far, but I don't know how far. You can see the influence of these high tides going, the opposite way inland. I wonder about this because of the signature of marine water with your diatoms, and it's just a question locally how far the high tide has an influence in outside the river, because you can see the opposite flow, like going the tide inland, right?
Yeah, thank you for your question. Yeah, it's certainly definitely a concern. However, from interviewing with local residents who had been there, there was even an individual who could somewhat remember the 1960 tsunami and earthquake. From talking with these local residents, it seemed that local flooding from tides and daily tides and monthly tides even were not really a concern where we were doing our investigations. And so then the biggest concern was occasional flooding and having that freshwater signal. But I think because we saw anomalous marine diatoms or mixture of diatom assemblages within these sand beds, it points a little bit more towards the argument that these are more probable tsunami deposits, not just from freshwater flooding.
Okay, next question is from Professor Pedro.
Oh, thanks a lot, Isabel, for an excellent presentation. I just have, I'm a bit intrigued on the thickness of layer 5, because it seems to be that it was the thicker one. Is there any relationship with the magnitude or the intensity of the earthquakes that caused that?
Thank you, Pedro. That's a very good question to ask as the next step forward from this paleo-tsunami research that was done here. And unfortunately, I don't have a very satisfying answer for you as far as modeling of that 1751 earthquake. But I think if I can pull back a slide here, the information that I can provide you then are these historic estimates of the rupture length, and that the shaking was considered to be pretty strong and there was a high tsunami, but I don't believe that there has been efforts to model the 1751 earthquake. I could be wrong, but I don't believe that it's there. So I can only just provide you sort of these qualitative descriptions of what we know of the 1751 event.
The next question is from Dr. Pedro.
Hi, Isabel. Thank you for your nice talk. Especially about Kidiko. It's one of my favorite places in the world, with the little light tower and the sunsets there. And right regarding that light tower, I have one question. Is maybe this rock spit there being somewhat of a sheltering thing so that the tsunami is not entering so deep into the Kidiko River? And the second thing I was just thinking about, did you check maybe also the oxbows of the Rio Kidiko? Because for example, older tsunami deposits, because I think oxbows might be quite a well depositional area for sand also.
Yeah, the coastal morphology of this site in Kidiko is certainly a consideration that I had thought about as far as potential preservation of these historical deposits. There were slightly more, by slightly more, I just mean one more, two more tsunamis from the northern rupturing events that were preserved here, but that could also just be a result of the fact that these ruptures were much closer to Kidiko. So it's really difficult to say exactly if it's an issue of we just have ruptures that are occurring much closer to Kidiko versus the geomorphology location that's potentially affecting or biasing the preservation of tsunamis at this location. And as far as your question about the digging deeper into these oxbows and abandoned meanders, fortunately, we got just really stuck due to the water table at this basal sand 6, and we couldn't really get much deeper than that at the time of the investigation. But I agree that I think there's potentially possibility of older deposits to continue to investigate at the site. Yeah.
Any questions from anyone apart from this? Okay, so there is no question, I think. So before calling it a day, I would like to thank everyone for coming to this Namilinks kickoff meeting. And I'm very thankful to Professor Brian F Atwater, Professor María-Teresa, Professor Pedro Costa, and Isabel Hong for their presentation and support. And we'll see you tomorrow. Before saying good night or good morning, is it possible to turn on your videos so that we can take a picture of everyone? Smile, please. Yeah, coming. So most of them went for sleep. So few left right now. So I'm taking one more pic. So thank you, everyone. Again coming. People are coming again. Please wait for one more moment. Yeah, it's very happy to see you all. So expecting your cooperation in future also. Yes, thank you so much, and have a good day and good night to everyone. See you tomorrow. Bye.
Thank you.
Thank you. Bye-bye.
Bye.